Okay, so we've been practicing optimization. This is basically day 3. We've done um, basic area and volume equations where we're given a shape and we just use the equations that we already know. So today we're going to be actually creating our own equation. Okay, we're going to be using cost as well. So instead of just using volume and area or surface area or something like that, we're actually going to be creating our own equation. So here we go. We have a sports complex and we want to enclose 3 adjacent equal tennis courts with a fence that costs about $20 per linear meter. The budget of the fence is $12,000 and the dimensions of each tennis course, find the dimensions so that each court maximizes the area and find that maximum area. Okay, so let's draw a picture so that we kind of see what we're dealing with. Okay, so here we go. I don't know what it's doing, but it's not cooperating. So I guess it's going to want me to do each one by itself. Okay, so here we go. There's that. And then, so we're drawing these tennis courts. And we have 3 tennis courts. So we're going to divide this space up into 3 courts. Okay. So for you OCD kids, I'll make them more even so that it doesn't freak you out. All right, so here we go. We got our 3 courts. Okay. So what is our primary equation? So in these optimization equations, we have our primary equation. So primary equation. That is whatever we're optimizing. So in this case, we're optimizing area. So area, since we're doing length times width. Okay? Now, what is my secondary equation? Now, my secondary equation is my constraint or my limiting factor. So what is keeping me from building as big as courts as I need? And that is my cost. Okay? So I'm trying to maximize my area, but my cost is limiting the amount of area I can create. Okay? So let's keep it simple. And let's say that my vertical, this distance, are y values. So I've got 4 fences here that are y. And then these are x values. Okay? Horizontal distances. Okay? So I'm going to use these x's and y's to create my primary and my secondary equation. For instance, my length and my width. So let's say that this right here, this is my width, and then this whole thing here is my length. So my primary equation, basically, now area is length, which is 3x, times my width, which is y. Okay? Now my secondary equation is cost. So it's going to cost me $20 per meter, okay? And I'm going to multiply that by the fence that I'm going to be using. Well, I've got 4 y length fences plus 6 x length fences. So we'll start there. Okay? So that is my total cost to build my fence. All right? Now, to optimize my area, I have to take the derivative, which means I need it all in terms of one variable. So what I'm going to do is I'm going to use my secondary equation and get it in terms of one variable and plug it into my primary to put my constraint into my optimization. Okay, so I know that I can only use this much money. That's the cost, my total cost that I can use. And then here, I'm going to get 80y plus 120x by simplifying. Okay, and you can solve for either x or y, but I'm used to dealing with x's, so I'm going to solve for y. And when you solve for y, of course, you're going to move the 120x over, divide by 80, and that means that you get, so it's 12,000 minus 120x over 80, and when you simplify, you're going to get 150 minus 3 halves x. So that's my y. And now I'm going to take this equation, this y, this right here, and I'm going to come up here and plug it in to my optimization equation. Okay? So that means my new area equation is going to be 3x times 150 minus 3 halves x. Okay? So now I'm in terms of one variable. Not to mention my area now is being limited by this constraint from my secondary equation. So now we do the calculus part. So we got to find the maximums of this function. Well, to find maximums or minimums or critical points, you take the derivative and set it equal to 0. So when you multiply this and you take the derivative, well, maybe I should do that first. So let's just simplify first, because that's usually what I would tell my kids to do. So we simplify. So we get my area equals 450x minus 9 halves x squared. Because if I skip that step, I'm going to lose some people. Now I take the derivative. So a prime, 450 minus 9x. Set it equal to 0. So 450 equals 9x, which means x equals 50. So that's one of my dimensions for my tennis courts. Okay. Now I'm going to use that over here to find my y value. So 150 minus 3 halves and plug in 50 for x, and that'll give me my y value, which is 75. Okay? So those are my dimensions. So now I know that each one of these, x is 50, y is 75. Okay? So we found our dimensions. It also tells us to find the maximum area. So now we're going to use this equation here to find my maximum area. So area max is going to be equal to 3 times x, which is 50, times y, which is 75, which gives me 11,250 square meters. And that is my maximum area. Okay? So, again, we've been doing these problems, these optimization problems. So the steps basically is you find your primary equation. You find your secondary equation. You use your secondary equation to get your primary equation into terms of one variable. Then you simplify, find the derivative to find your critical points, and then use those critical points to solve whatever question they're asking you to find. Now, sometimes we'd have to use our endpoints, but in this case, our x values basically can be anywhere between 0 and whatever 1200 divided by 20 is. Okay, but obviously if x is 0, our length would be 0, which means we wouldn't have an area at all. And if x was on the other side, it would be basically no width. So on these problems, 9 times out of 10, you're not going to be dealing with the endpoints. Now, some cost problems you will, but not on these. Okay? Optimization.